everyone, welcome to the Specialist 1-2 lecture. Hopefully you're all excited to learn some new stuff today. Okay, so my name is Michelle. I graduated in 2018 and I'll be talking through all the Special 1-2 lecture today and kind of exploring the concepts with all of you. So my subjects in VCE were mainly maths and science subjects, so I did bio, methods, spec, chem, physics, and mainstream English, and I thought all of the subjects did kind of help with each other, especially because there was a lot of greater overlap when I went through compared to now, but essentially all of the problem solving skills and all of that type of thing is very transferable regardless of what university subject you really go into. So it's really good that I think you're doing Specialist 1-2 now, because it involves a lot of lateral thinking and deeper application of the concepts. So I'm currently in my final year of med right now, and I kind of still do use all of that constructive thinking and problem solving skills that I would have used in VCE as well. So just use a quick thing about HR Notes. We've been around since 2007, and our mission is to make sure students like you can be supported as much as possible. So we have tons of resources available, so make sure to check those out. And we've been doing all these lectures since 2015, with some of them being online and some of them being in person. And they've worked we've constructed them so that it's accessible to as many people as possible. They're interactive, so do ask as many questions as you'd like. So talking a little bit more about the free resources that are available from HR Notes, do have a look. There's a lot of booked based resources with our study notes, newsletters and articles, which are designed to kind of help you think about certain questions and concerns, and especially the articles as well. Some people have advice on to how to get into certain university courses, and those are really helpful as well. And their study notes, especially for a subject like this where you're allowed bound notes, is super duper helpful. We also have lectures just like this, and we also have short videos as well, just talking about some tricky concepts. And if you ever have any kind of questions or anything really, you can always reach out to us on our forums and discussion pages, and we'll be definitely more happier than ever to kind of answer your questions. So definitely have a look into those. There's also other things which are offered by the HR Notes group as well, like Choose Smart, Study Guides and Edu Unlimited. So if you feel like you need a little bit more help in certain areas or just would like a couple more resources to use, make sure to look into those. I'd like to also extend a special thanks to La Trobe University and our other university sponsors as well, like RMIT, Deakin, UTS and Macquarie University. They're all doing it for your benefit and really helping us to provide these education and lectures to you. So make sure to check out their early entry programs and see whether you're interested and have a read up about them. Okay, amazing. So Specialist Maths, congrats for all choosing this topic. It's one of the trickier topics, I would say, in VCE in general, just because especially with the change of the study design as well, it's been made even a little bit more trickier than it used to be. So congrats on making it through the first term. It's the first stretch of Specialist Maths, and I know it can be really scary and daunting at first, but just know that everybody is here to support you, and if you have any questions or any concerns really at any time, you can reach out to people who've done it before, and they'll think about their similar experiences that they've had. So make sure to kind of ask lots of questions, be curious, and it will benefit you. So essentially a lot of the Spec 1-2 stuff is carried into 3-4, and in fact I would say Spec 1-2 is actually probably even a little bit more difficult than 3-4, in that definitely the 3-4 questions are more difficult to do, but in Spec 1-2 you're learning about all these new things that you've never really heard about before and never really had any exposure to before. So it's a really hard time, and there's just so many new topics as well that you've been bombarded with. So it's really good that you're trying out this subject and seeing all the different subjects and kind of little subtopics that are involved in that, because it is quite a tricky subject in general, so you'll see a lot of new things and a lot of new concepts, and don't be too concerned if you're not 100% at them by the end of this year even, because next year all of the topics that will be assessed on the exams and assessed on your SACs will be kind of gone over again. So some of it will be taken as kind of knowledge that is implied over to next year, like shapes and things, but for a lot of the stuff like complex numbers, vectors, logic and proofing, calculus, you'll do a little this year, but then you'll really actually get stuck into it a lot more next year. So this year I want all of you to focus on kind of knowing the universe of every little subtopic you learn. So kind of just getting a brief understanding of complex numbers, how they work, why we have them around, how to briefly solve them, all that kind of stuff. Like, and then don't really get stuck too down into the nitty-gritty details. I think it's just important for you to have an overall understanding of the language of each of the topics you look into. But obviously if you do want to get started down into the nitty-gritty, by all means, but just be a bit careful, especially in the topics of complex numbers and vectors, because even as a 3-4 part of the 3-4 component to it, it doesn't actually go into too much detail into the universes of those two things. So if you find yourself falling down a rabbit hole, just be a bit careful in terms of vectors and complex numbers, because the more you research about them, the more you realize you don't really know about them, because they're very big topics and they get done during university as well for people who pursue degrees that involve mathematics. So they can get a lot more complex than the stuff we do. So just make sure you don't fall too far down the rabbit hole, but always, explore your interests. Cool. Alright, so let's get on with the lecture. So what we'll be going through today is just a bit of algebra, which will also be useful for methods as well. We'll be talking a bit about complex numbers, and that's the new number universe which is introduced to us. And we'll talk a little bit about series and sequences as well, which is also a 1-2 specific topic, but unfortunately, so it used to be, because logic wasn't part of our study design, logic and proof was a part of our study design, so series and sequences would very rarely come up as a 3-4 accessible thing. But now, since logic and proof has come in, especially in something called proof by induction, the series and sequences can come in and can be assessed, because it's a good proofing type of question to do rather than really assessing, the actual your ability to do these series and sequences. It's more testing your ability to prove around them. But it's really important for you to get a baseline knowledge of them, because otherwise it's going to be a bit difficult to prove around them as well. Cool, so how this lecture will run, we'll just do a bit of an intro, which was what we were chatting about before, and then we'll go through all of these 3 blocks of content. Please do ask lots of questions. I really encourage lots of questions, because you can kind of find out new things, and then if you have that question, I'm sure that a lot of other people would have the same question as you. And don't ever stop yourself from asking a question, because curiosity will mean that you learn the stuff more deeply. And don't also be afraid to answer any questions or have a go at any of the questions that we go through today, because if you get it right, great, you know that you're developing a great method to do these types of questions. If you get it wrong, no worries. It means just that you'll learn it more deeply for next time. Cool. Alright, so let's talk about algebra. This is a bit of a mathematic meme, so we'll get stuck in. Alright, so algebra is essentially the study of mathematical symbols and this whole group of rules that we use to manipulate these symbols. So in high school, it's mainly about learning the different techniques that we'll use to manipulate and solve equations, like linear simultaneous equation, decomposing into partial fractions, that type of thing. So it's really about learning the different techniques and kind of the basis of the techniques to really help you manipulate at the base level. In high level algebra, there's more in-depth study of things that, we look into kind of. So in high school, we kind of just assume that those techniques are a thing, right? It's kind of like learning the formulas for things versus having to prove the formulas. So if you want to do it in university, or if you're interested in that type of thing, you might be asked to prove things that, we kind of took for granted. Okay, So let's talk about simultaneous equations first. So simultaneous equations are essentially, like the name suggests, when we have two equations simultaneously. And it's essentially just when we have like two or more equations, and we're often trying to solve for multiple variables. Generally, the number of simultaneous equations has to correlate to the number of unknowns. So you can have more equations than variables, but the only thing you need to be careful about in that type of case is that if you have more equations than variables, so you do all your solving, do all your magic, and then when you sub it into the last equation that you haven't used yet, you just need to be really careful that it works, because sometimes the goal of the question is actually for you to prove that something isn't working instead of it is working. So we have simultaneous equations is a thing that's throughout methods, and you would have been doing kind of pre-VCE as well. So hopefully the ideas and the concepts behind it sound quite familiar to what you think. But let's go through a couple of these questions. So these are linear simultaneous equations. Ooh. So these are our linear simultaneous equations, and you'll see on your calculator as well, you're able to choose between like linear simultaneous equations versus your kind of more complicated simultaneous equations. So, or anything non-linear essentially. Okay, so the general methods that we can talk about substitution or elimination. So maybe let's talk about just doing both as a bit of an intro to simultaneous equations, and a bit of a reminder about what's really going on. So let's talk about substitution first. So in substitution, what you want to do is rearrange one of the variables in terms of another variable, and then you can kind of substitute it in after that. So let's rearrange this. So x is the subject. We'll get that 2x will equal to 3 minus 3y. So therefore x will equal to 3 minus 3y over 2. Okay, and then we substitute, like the name suggests, into the next equation. So we'll get that this is 5 times 3 minus 3y over 2 plus 4y will equal to 11, right? So we'll get 15 over 2 minus 15y over 2 plus 8y over 2 will be equal to 11. So if we kind of look into that, we'll get that this is 15 over 2 minus 7y over 2 will equal to 11, which means that 15 over 2 minus 22 over 2 will equal to 7y over 2. So we'll get this is negative 7, right, will equal to 7y. So y will equal to negative 1. And then when we substitute that back into there, so we'll get this is 3 plus 3, so that's 6, so x will equal to 3. Cool. Let's talk about the elimination method. So elimination, you are aiming to get rid of one of the variables, and you change the whole equations and kind of minus the equations as a whole. So what we can do is we can times the first one. So if we name this one 1 and this one 2, we can times the first one by 5 and then minus away from the second one times by 2. So what we'll get is this times by 5 will give us 10x plus 15y will equal to 15, and that will be minus this times by 2, so that will give us 10x plus 8y will equal to 22. So once again, we'll get that 7y will equal to negative 7, and y will equal to negative 1. So therefore, if we substitute that back into here, into one of the equations, we'll get 2x minus 3 will equal to 3, so x will equal to 3. Or you can even substitute into the bottom equation as well, because you'll get 15x will equal to negative 5x minus 4 will equal to 15, so you get x equals to 3 as well. Okay, let's try this with a little bit more complicated. So in this case, it's not really going to be possible for us to use the elimination method, because we have different, the x squared, y squared versus the x by itself. It has different powers on it, so we're not really going to be able to cancel out the terms unless we try and square and try and do something funky. So the easiest thing to do for this one, it would just be to substitute. and it already has it in the form of y equals to x plus 4, so that's really beneficial for us because we can just go x plus 4 all squared will equal to 26. So we'll get that this is x squared plus 8x plus 16 will equal to 26. So we'll get that this is 2x squared plus 8x minus 10 will equal to 0. So therefore we'll get that x squared plus 4x plus 4x minus 5 will equal to 0. So we can get an equation of x plus 5, x minus 1, and that equals to 0. So we'll get that x equals to negative 5 or x equals to 1. And we can check, is there any restrictions on what we can take? Nope, not really. So if we try and sub this into our y, this would mean that y equals to negative 1 or y would equal to 5 here. So you can kind of see how it switches in terms of the positions, and it kind of gives you the same result in the end. And that's just because of this one, the x squared plus y squared relationships. That's why it kind of looks like the numbers are switching positions there, with the positivity and negativity of them. Cool. Awesome. All right. Okay. So we want to solve for s in terms of a only, and we've got these two wonderful equations that we're trying to deal with, right? So we have as equals to s plus h, and then ah equals to a plus h, right? So the first thing that we want to do is replace. So we want to replace the h so that h is gone, right? That's our first goal, to get rid of it. So what we can actually see here is that if we took away this, right, because we want only as, right, we don't want so we need to replace the h's away. So if we say h is therefore equal to as minus s, we'll be able to substitute that back into here. So we'll get that this is going to be a times as minus s equals to a plus as minus s, right? So we'll get a squared s minus as equals to a plus as minus s. Okay, so then we want to get all the s's on one side, so we can kind of divide through by that. So if we try to divide all of that onto one side, we'll get this is a squared s minus 2as plus s equals to a. So if we divide that by s, we'll get a squared minus 2a plus 1 equals to a. And then we'll get s will equal to a over a squared minus 2a plus 1, right? Or otherwise known as just a over a plus 1. Sorry, a minus 1 squared. Minus 1 squared. Cool. Awesome. And then you can kind of just make sure that's true. So, well, you can even just try and find out what h is, I guess. But from our work here, that's essentially what we're doing. So we did a bit of a substitution for this one, because we moved the s across and then we subbed it in. So we got a times as minus s, and then plus a plus as minus s. And then once you get that, you can kind of rearrange from there onwards to really get the equation that you're looking for. And yes, that is it. Cool. Alright, so next is asking about the area of the shaded region. And it's important for us to kind of recognize what region that they're asking for. So they've mentioned the shaded region here, which is this section out here, right? So what we can do is we can try and find, so there's not really an easy way to find the areas of these little bits, right? So what we can do is that we can actually find the area of the whole circle and then find the area of the middle part, like the square, and then just cut that middle part out. So if we talk about what the area of the circle is, the area of a circle is pi r squared, and our radii here is just r, so therefore our area of circle is equivalent to that. Now, let's talk about area of the square. Our area of the square is equivalent to base times height. So base times height. We note that this is 0, so that kind of means that this would also be r, and this would also be r, and this would also be r. And from there, because we need base times height, we can kind of form a little triangle that has r, and then the Pythag of that. So it's going to be root r squared plus r squared, which is going to be equivalent to saying that one of these sides is going to be equivalent just to r root 2, right? Because it's just 2r squared, so r root 2, and therefore this side is also equivalent to r root 2, right? So then we can kind of, because we know that this is exactly from origin, it touches the edges at that point. Okay, so then what we can do after that, once we get the r root 2, so these two r root 2's kind of can times together, so we'll get that this is r root 2 times r root 2, which will give us just 2r squared, whatever that is. So then after we do that, we now need to find the area of the shaded region. So the area of shaded region is a circle minus a squared. So therefore you can say a shaded will just equal, so we'll just get this, that is going to be pi r squared minus 2r squared in terms of the shaded region. So we kind of find what the outside and then also find what the inside part is. Okay, cool. Let's move on. Alright, so let's talk a bit about the discriminant. So the discriminant is also quite a useful measure both for methods and for spec. So what it is it's essentially used in a quadratic equation, and it's used to determine how many solutions we really have in a quadratic equation. So it's really, really important both in methods and spec, so it's good to have a lockdown on the knowledge of this. It's also quite useful for predicting whether a graph has real or complex solutions, because if it has complex solutions, we can kind of look into that further when we get to complex numbers. But it is possible to solve basically any quadratic if you're able to use the complex universe as well. But not all graphs will have just real solutions. Some graphs will only have those complex solutions. So it's important to note that. So the rules that we have here, so for ax squared plus bx plus c, the discriminant we get is that it's b squared minus 4ac. So if that, and that's kind of just derived from the quadratic formula, so x equals to negative b plus or minus b squared minus 4ac over 2a, right? You can see that the b squared minus 4ac part is the part under the square root, so that kind of gives you a sense of why it has to be bigger than 0, because if it was smaller than 0, therefore your square root wouldn't exist, and if your square root doesn't exist, then your overall solution also doesn't exist. So therefore that's why we have to make the discriminant bigger than 0 for that. Now if it was smaller than 0, we can't have a negative surd, so that unfortunately does not exist. But if we have an equation which is just one solution, what we will have is just b squared minus 4ac should just equal to 0, right? And why that is because when it will only have solution is because that part equals to 0, it will no longer have that plus or minus function, so it will kind of just be the negative 6, or the negative b in this case, the negative b over 2a. So basically the position of the y turning point will tell you where the solution is, as long as the graph hasn't been horizontally translated. Alright, so the first one is prove that there are always real solutions to the equation shown below. So first of all, we're going to try and work out what b minus 4ac is equal to. So ignore the actual b's and c's in here, and we just need to focus on copying it accurately across. So it's a plus c squared, so 4a plus c all squared, and then we'll have minus 4a, which is going to be negative 8 when we bring it to the other side, c, which is negative b squared minus 2ac. So therefore what we'll get from this is that we'll get that this is going to be 16a squared plus 8ac plus 16c squared plus, oh, is it plus? Sorry, let me just rub it out. So we'll get that this is going to be 16a squared, this, and then we'll have here that this is 4ac, so b squared minus 2ac. So this is going to be 8ac, and then we're going to have plus 16c squared, right? Okay, and then we'll have plus 32b squared minus 2ac. Okay, so then what we have to do is kind of complete this equation that we've got here. So that's going to be, so 4ac, negative 4ac, and then we have minus 8 minus this times by this. Okay, so we're going to end up with 16a squared plus 32, sorry, not 8, 32, so that's going to be 16 times 8, so that's going to be quite big, so it's going to be 16 times by 8, because we'll have this, I think I only times half of it by 16, whoopsies. So let's just make the 16 on the outside and then times it in, rather than doing that. 16a squared plus 2ac plus c squared plus 32, all of that. So we'll get that this is 16a squared plus 32ac plus c squared plus 32b squared, and then we'll have that this is going to be minus 2ac, so minus our 32 times by 2ac, which is going to just be 64. Minus our 64ac, right? Okay, so we get a squared, so we get that this is going to be 4ac squared, so we'll get 16a squared plus 2ac plus c squared, and then we'll have minus 4ac, so minus 4, negative 8, 2ac. Okay, cool. I have a feeling that this question was meant to be, so it's just ac, but that's right. Let's have a look at what we would get in the end. So we would end up with 16a squared plus c squared, plus 16c squared plus 32b squared minus 32ac, right? Okay, so then we have to kind of predict what's going on here. I think that what was meant to be going on here is that this b squared minus 4ac component, that should have been, because that's going to be your a, and then when you times it by your negative 8 there, we can see that I think the idea of it was that the b squared should have cancelled out, so sorry about that. We'll just pretend that this is ac instead, because there's not always going to be real solutions to this, because if there was always real, there's only real solutions if we know 16a squared plus 32b squared plus 16a squared, if we know that that is going to be bigger than 32ac, because potentially we could have had like A, B, C all equal to just to 1, right? Or yeah, it could all equal to 1, it would still be overpowering, wouldn't it? But that's right. So essentially, if we pretended that this was just instead just AC, so that we got 4AC, so we have B squared minus AC, so therefore we have 32, right? AC, and if we kind of write that in, we'll have that this is 16A squared plus 16C squared plus 32B squared, right? And we can say any number squared is bigger than 0, so therefore we will know that this discriminant is always going to be bigger than 0. Okay, so we need so for the conditions for only one solution, right? If we consider something like 16A squared plus our 16A squared plus our 16C squared plus our 32B squared. That was our solution that we had there. So if we kind of consider that and we just need overall one solution that to work with, then what we can be considering is that we would need A to equal to 0, B to equal to 0, and C to equal to 0, right? Because that's really the only possibility for us to get one solution for this. Otherwise, we'll always have more than one solution because nothing squared should it be equal to that. Alternatively, if we kind of follow the old one and we had 16C squared plus 32B squared, right, minus 32AC, all of these would, by any number, if they are not 0, they are always going to be greater than 0, right? So this is going to be the positive component, and this is going to be the negative component. So we can kind of simplify that down to saying that that's C squared plus B squared plus 2B squared, minus 2AC has to equal to 0. So if we can kind of take that out, that would mean that we need, in some form of the other, when we're trying to solve for something, that's the kind of the relationship we need. So that's the relationship we need between all of those numbers, right? So if they're all non-zero numbers, that's a relationship we need between the numbers. Cool. All right. So let's try this with the smallest positive integer, so that 3x squared plus px plus 7 equals 0 has real solutions. So what we want to do here, once again, we want discriminant b squared minus 4ac, so therefore we'll get that this is p squared minus 4, 3, 7, right? And we'll get this is p squared minus, so that's 12, that's 21 times 4, so that's 42, and then 84, so p squared minus 84. So if we want this to have real solutions, we need p squared minus 484 to be bigger or equal to 0, right? So what that actually means for us is that p squared has to be bigger or equal to 84. So if we consider like our graph of p squared, right, let's say 84 is here, that will mean that if we try to solve p squared equals to 84, we'll get that this has to be p is equal to plus or minus, and we can kind of use the roots that we've undone here since we've already have that here. So it should just be 2 root 21 in terms of the roots of it. So therefore we can kind of see that this is going to be negative 2 root 21, and this is going to be positive 2 root 21. And this is just a general tip for like any inequality where you're not using a linear equation. You must always just kind of graph it out, because once you graph it out, you'll actually be able to see what's going on in the overall perspective of what's going on. Because if you don't graph it out, there might be unexpected turning points or things which are going on which you don't really foresee. So when we look at this, we'll get that this is 2 root 21, and this is 2, so this is negative 2 root 21, this is positive 1, and because it wants the smallest positive integer, we're only looking at this side, and we need 2 root 21, right? Okay, so because we're looking for an integer value, this third must be, in order for us to be like for p squared for this to be greater or equal to 0, it must be past that point, right? And because we're looking for an integer value, we need to look for this third to be an actual value. And the next closest one where we get an actual value will be 2 root 25, right? Because if we go backwards to 2 root 16, that will be under here. So that will mean that p squared is not bigger than 84. So we won't be able to have a sufficient number. So the next closest number will be 2 root 25, which is essentially just 2 times 5, which we get 10. So the smallest value of p, smallest integer value of p, is going to be 10, right? Cool. Alright, so let's move on. So then if we kind of look into here and we want, so now if we want the equation of x squared plus 4kx plus 3k, where k is a constant, has distinct real roots, and we want to prove that k bracket 4k minus 3 is bigger than 0. So what will happen here is, once again, we are talking about the roots and kind of what's going on. So because we're trying to talk about the roots, essentially what we have to do is talk about what the discriminant is first, right? So the discriminant for this question would once again be b squared minus 4ac. So we can pop everything in, so we get that this is going to be 4k squared minus 3k. Okay, so then we'll get that this is 16k squared minus 12k. Alright, so if it needs to have distinct real roots, so real roots, because it has an s there, that means that we need 2 roots, right? So when we need 2 roots, remember discriminant has to be greater than 0 for 2 solutions, right? So that what that means is we need 16k squared minus 12k to be greater than 0. Okay, so we can take away the 4 and we'll just get 4k squared minus 3k has to be greater than 0. So we'll get that 4k minus 3 has to be greater than 0, as we needed. Right here. Alright, one more. So it has to find, you want to find the set of possible values. So we're using our equation from before. So we need 4k minus 3, I think it was. Yes, has to be greater than 0. So once again, if we kind of expand that out, 3k, and we wanted to draw out, because remember our inequality is with something which is not linear, so we must draw it out. So we can kind of note here that it's going to go through 0, right? And the other intercept that it's going to go through is 3 on 4. We note that it's a positive graph as well, so we can kind of draw it something like this. So it'll go through 0 and 3 on 4. So you can kind of note how it travels in both directions. And it wants the possible values of k. Now there's a number of ways that we can write possible values of k. And, you know, it doesn't really matter which particular way you write it, as long as you write the correct gist of it, right? So you can either say k is greater than 3 on 4, or k is smaller than 0, or you can write k is 3 on 4, so k belongs to 3 on 4 to infinity union with negative infinity to 0. Remember, all not including, because we can't include 0 here. And then also we can also write it as k is r except for, and we include these values because we have to exclude them from our equation, 0 to 3 on 4. So those are kind of 3 different ways to write it, and we would have talked about this, I believe, earlier in the year in the January lectures, potentially, on how to convert between the different sets and talking about the different notations. So just make sure you're comfortable with the different notations, you know, just in case they actually ask you to put it in a specific form. For example, if they said put it in the form r except from a to b, and you would be a bit stuck if you didn't really know how to convert through the forms. So just make sure you know how to write equations both in set and interval notation, because I find both of them are appropriate for different scenarios, right? I find that the inequality or kind of that type of notation is more helpful when you're solving for things, and because like you can directly see what's really going on, whereas I find the interval notation a bit cleaner to work with, so that like at the end it just looks a bit cleaner as an answer in my personal opinion. But it's up to you which part, like which way you use it really. Okay, cool. So let's kind of talk about this one a little bit. So partial fractions are essentially partial fractions will unfortunately haunt you through the rest of your mathematical specialist maths journey, and it's used when we're working with rational functions, so i.e. when we have quotient of two things. So when we have q of x over p of x, right? And we can kind of decompose the partial fractions from there. So what we want to do here is, for example, if we had something like this, we want to find different methods on actually how we're going to do that, right? Because we've gone from here to here, and this in fact is definitely the correct decomposition, but we want to know how we actually got from here to here, right? So a good thing to learn how to do early is partial fractions. It comes up really important when you go into next year when you're doing calculus. It also comes up importantly when you're trying to graph rational functions as well, because by decomposing it, you can kind of see the different relations and different equations. Because even though this might not be that easy to graph, right, because it's two different functions basically put together, this is even harder to graph in my opinion. So by composing it like this instead, we can kind of see the different things that's going on compared to this where everything's kind of just muddled all together. So in terms of partial fractions, the first thing that we need to do is look at its denominator and then look at the factors, right? So we need to do a bit of magical long division or short division or synthetic division. We just need to do some sort of division to really factorize our factors that we have. And then we can use these rules. And I would recommend having these rules somewhere in your bound notes, just basically anywhere in your bound notes, but just to have at least one copy of this. There's a lot of resources floating around which have like this in different tables essentially. So my best recommendation is choose the table which looks the prettiest and easiest read to you, and just use that table and make sure to have it in your notes somewhere. And in fact, you can use this table if it's pretty enough for you as well. So how I like to think of partial fractions is a little bit of a jigsaw puzzle. So what you're doing is kind of just putting everything together into a puzzle. So if you have just a linear x factor by itself, you can pop one of those in. If you have a repeated linear factor, you can kind of add that onto the end. And then if you have a quadratic, you can kind of add that onto the end as well. So if we had something which was like 1 over x squared plus x plus 1, which we know is an irreducible quadratic because b squared minus 4ac, so that's going to be 1 minus 4, so it's going to be irreducible because it's smaller than 0. Let's say we had x plus 1 squared, and then we had x plus 2. So let's say we had something like that. So if we wanted to decompose it, we know we have a linear factor, so we can start by chucking that in there. So x plus 2. We also have a repeated linear factor as well, so we're going to say that's b over x plus 1, and then we're going to repeat it as many times as we need to kind of get to the equation. So that's squared, and then we add the quadratic on as well because that's another one of the factors. So the funky thing about quadratic is dx plus e rather than just like a or b, just like a single letter. It's dx plus e. How I like to think of it is that always the denominator is going to be one more power than the numerator in these partial fraction type things. Okay, cool. So then we'll have that's going to be over x squared plus x plus 1. Okay, amazing. All right. So let's try and decompose this one. So I'll pop this one into the chat and give you maybe 20 seconds or 10 seconds to kind of consider what we need to do here. So I'll just give you maybe 10 seconds to have a little, or 20 seconds, let's say, to have a bit of a think. Cool, awesome. All right, so we can kind of see what's happening here. So the first thing that we want to do is decompose the kind of the denominator. So we'll have this is going to be 10t squared plus 13t minus 3. We can do a bit of cross multiplication or try and figure out what's going on. So we know that the factors have to times to kind of give us 30. So the front two have to times to give us 10, and the back two have to time to give us 3, and the middle part has to be 13. So we can kind of break this up into 10t squared, let's say minus 2t, and then we'll say plus 15t minus 3. So if we break it up like that, we can take away 2t at the front of this one, which will leave us 5t. That's very squished together. So that will leave us with, so if we take out 2t, that will leave us with 5t minus 1 plus, if we remove 3 from there, that will also give us 5t minus 1. So then if we group the things together, that will give us 2t plus 3 and 5t minus 1. Okay, so essentially now we have 8 minus 3t over 2t plus 3 and 5t minus 1. So hopefully we were able, so if we looked at this, we can identify that we need, two linear factors. So we'll have a over 2t plus 3 plus b over 5t minus 1. Okay, so then we times everything across, so we get 8 minus 3t will equal to a 5t minus 1 plus b 2t plus 3. And the best thing to do here is that we need to look into, so there's kind of two methods of figuring out the actual values of them. So the first method is like simultaneous stuff. So the first method is simultaneous. So what we do is we'll get 8 minus 3t will equal to, and then we kind of group. So we'll have t 5a plus 2b. And then we'll have the normal part of it. So we'll say plus negative a plus 3b. And we equate those coefficients across. So we'll have 5a plus 2b will equal to negative 3, and negative a plus 3b will equal to 8. And then we can kind of do simultaneous equations on those two. Alternatively, the other method is we sub values in. So you sub in the values for what you're going to get here. So if I subbed in 1/5, right? T equals to 1/5. T equals to 1/5 would cancel out what that part is. So I would just get 8 minus 3 over 5 would be equivalent to b times 2 over 5 plus 3, right? So 8 over 5, that's going to be 40. 40 over 5 minus 3 is 37 over 5. And our b component is going to be, so that's 15. So that's going to be 17b over 5. So we're going to get that, when we try and cancel that out, we'll get that b is going to be equal to 37 over 17, which is a bit of a gross number, but can't really be done. And if we tried to do the same thing here, we could multiply the bottom equation by 5, so we end up with 5a plus 2b equals to negative 3, and negative 5a plus 15b would equal to 40, right? So when we times everything across, then we'll get the same thing. So we'll get 17b will equal to 37. And that's what you can get there. And then we can, so for this, once we do that, there's benefits to both, right? Because then once you sub it, you can just directly sub it into here to get what you want. And then for this one, we would have to sub in t equals to negative 3 over 2, right? To get rid of this one, so that we only end up with the a component now. So then now we're going to get that 8 plus 9 over 2 will equal to negative a times negative, let's rub out so we have more space. Let's just erase all. So far we've gotten that, let's just write our equation one more time. So that's 5t minus 1, 2t plus 3. We said that's equivalent to a over 2t plus 3 plus b over 5t minus 1. So we got 8 minus 3t is equivalent to a 5t minus 1 plus b 2t minus 3 plus 3, sorry. So we've gotten so far that b equals to, I think it was 37 over 17. Yeah, I think so. So that was 37 because that would have been positive. That would have been, yeah, so it's positive. And then we get our a component. So we're subbing in 2/3 before. So 2/3 here would be, oh sorry, 3 halves, negative 3 halves here. So we're subbing in t equals to negative 3 over 2. And we'll get that this side equals to 8 plus 9 over 2. And the other side equals to a times negative 15 over 2 minus 1, right? So we'll get that this is, so that's 16 over 2. So we'll get this is going to be 27 over 2. Oh no, not 16. So yeah, so 25 over 2. So we get 16 plus 9, so 25 over 2. And that's going to be equivalent to negative 17 over 2. So we kind of can take out the 2's, but then we'll just get that a will equal to 25 over negative 17. And in the previous one, we got that negative a plus 3b would have equaled to 8. So we can kind of, we already knew what b was, so we could have substituted into there. So we get negative a plus 3b, which is 100, and so that's 21 times that, so 21 plus 90, so 111 over 17 equals to 8. So when we kind of put that across, so when we times 17 by that, we'll get that 7 times that is 56, and 8 times that is going to be, so 8 times that is going to be 80. So 80 plus 56 is 136. So 136. So we'll get that negative a equals to 136 minus 111 over 17, which means that a would have equaled to negative 25 over 17, like this one suggested. So there's kind of two different methods. So this is the subbing method, and this is kind of the elimination simultaneous equation method. Cool. Alright, so let's chat about this one a little bit more as well. So this one is, once again, our partial fractions, and what we're trying to do first is we want to kind of expand the denominator, or more factorize the denominator until we can get something where we've decomposed it all into our factors. So our x cubed plus 9x is going to be equivalent to x squared plus 9. If we check the discriminant of that, that's going to be 0 minus 36, so it's smaller than 0. So therefore we can kind of move on from there. So we'll get that this is 2x plus 4 over x cubed plus 9x. And a gimmick here, I guess, is that this is actually bigger than this, right? So we actually can't turn it into a partial fraction straight away. So what we need to do first is, because this value is going to be bigger than this, it's going to turn into an improper function if we try to do it straight away, and it's not going to work out terribly well. So, and also it's going to make it hard to kind of equate coefficients and do that. So what we can do first is kind of just divide across first and do a bit of long division. So we'll have x cubed plus 9x, and we'll have x to the power of 4 plus 0x to the power of 3 plus 0x to the power of 2 plus 0x, and then just plus 2 at the end. So we can put that in, and we'll get that this is going to be x, right? And so this is going to be x to the power of 4, and we're going to say plus 0x cubed plus 9x squared, and that's going to be just negative 9x squared plus 2, essentially. So if we look at that, that can't divide into it anymore, so that's the new thing that we're actually going to get. So this is going to just be equivalent to x plus negative 9x squared plus 2 all over x cubed plus 9x. So this is the thing that we're actually going to decompose. So when we try and decompose that component, we'll get that negative 9x squared plus 2 over x squared plus 9 will be equivalent to a over our x plus b x plus c over our x squared plus 9. So then if we kind of times across and make sure everything's times across, we'll get 9x squared plus 2 will be equivalent to ax squared plus 9 plus x bx plus c. Alright, so then we can, once again, we can either equate coefficients or sub in values. Either way is fine, essentially. So maybe we can try both ways just to kind of go over it one more time. So let's maybe do it via the simultaneous equation version first, and then we can go through together and we can pick up from this step and do it via the subbing values. So if we do it simultaneously, we'll get that negative 9 will be equivalent to a plus b, right? Because we'll have ax squared and then plus bx squared. And we'll have that 9a will equal to 2, right? And c will equal just to 0 because we can't see any c's. No pun intended, because there's no x component on that side. So we'll get that a is actually just going to be 2 over 9. So b, therefore, when we kind of put that across, because that's negative 81 over 9, so that will be, b will be negative 83 over 9. Cool. We can try doing the substitution method up here. So we can sub values in. So if we subbed in x equals to 0, this part would be cancelled out, right? And we would just get 9a would equal to 2, right? So therefore a would equal to 2 over 9. And then what we can do after that is try subbing just different values. So now x equals to 1. And we would get that this is going to be negative 9 plus 2, which is 7, is equivalent to, so we know this is 2 over 9 out here, and we have 1 plus 9, so that's going to be 10, so that's going to be 20 over 9, and then here we're just going to sub everything 1, so plus b plus c, and then from here we can also do x equals to negative 1, right? And that would give you the same thing on that side, right? 7, and would give you the same thing here, so that would be equals to 20 over 9. That would be negative, so we'll have minus c minus b, so we'll have just b minus c then, plus b minus c. So if we added those two together, we would have gotten that 40 over 9 plus 2b, because the c's would have cancelled out. And then when we kind of just move that onto the other side, so we want to find out exactly what b is. So when we kind of move that to the other side, we'll get that b is a certain value, so we can put that across. So it will be 20 over 9, and then so 40 over 9, we can kind of divide that across and times that across, and we'll eventually get an answer from there as well. So you can kind of see how the two different methods work out. But essentially it's up to you for either. To be very honest, a couple of these questions, I feel like the numbers are a bit gross, but you know, if the numbers were a bit nicer, be a bit more straightforward. But I guess you can get gross numbers as well, so fair enough. Alright, let's talk a bit about complex numbers now. So the complex number system is a number system which is outside of any numbers that we've used so far. So we've always worked in the real number system with our integers and our rational numbers and all that kind of stuff, but we've never kind of ventured outside that. So complex numbers is actually the outside the bubble, even bigger than that. So complex numbers actually include all real numbers. So the complex part of a complex number is the I component, and where I has come from is that we previously didn't really have the ability to talk about when the discriminant was smaller than 0. So what we're doing by using complex numbers is essentially we're just making it so we're actually able to do that. And how we're able to do that is by making I squared equivalent to -1. So that's what we get. And then so when we try and make a complex number, we have an imaginary component and a real component. So the imaginary component can be 0 and the real component can also be 0. So it can be 0 plus 0i, right? Or it can be 0 plus 3i, or it can be 3 plus 0i. All of those would still be defined as complex numbers. So the real important thing is that the coefficients of complex numbers must be real. So you can't have I plus I squared I. Like, that doesn't really make sense. It's going to simplify to either, it's going to always be simplifiable to either it's always going to be simplifiable, so there's a real component and an imaginary component. So we just really need to be like that's just one thing that always needs to be true. The coefficients always just need to be real numbers. Cool. Alright, so for the imaginary number, so for the complex number, z equals to a plus bi, well, there's two components like we talked about. There's the real component and the imaginary component, right? So because the coefficients are real, we can just say, if we're talking about the real component and the imaginary component, they are just the coefficients of the numbers, right? They're not bi, it's just b, because it's just talking about the coefficient of them rather than the whole thing. Okay, so let's go through a couple of the things that happen in complex numbers. So the first of all is, it's kind of just like learning a new universe of numbers, right? That we've previously done, and now we're going to venture into further. We can apply most of the algebra rules, because remember, real numbers are complex numbers. So most of the rules that apply to real numbers, we can kind of extend and change a little bit so that it becomes applicable to complex numbers as well. So essentially what we can do here is if we were pretending this was a real number, so if we had a plus b squared, we could simply expand that to a squared plus 2ab plus b squared, right? So what we're going to do here is we can do the same thing. We're going to have 4i squared plus 12i plus 9, right? So that's kind of the result we're going to have. The extra step we have to take in terms of complex numbers is simplifying it to make sure that we have a real component and an imaginary component. So in a complex number, you should really only have two segments to the question, right? Or as in, you should have just two parts. Like, we shouldn't have three things with different like I coefficients. It always should be simplifiable to two parts, because this one, for our I squared, remember the whole idea of it was I squared is equivalent to -1. So we're just going to get -4 plus 12i plus 9 here, which is equivalent just to 5 plus 12i. Okay, amazing. Alright, let's talk about this one. So a little bit more trickier this time. So we still do what we normally do in the universe of this. So we'll get that this is going to be I to the power of 5, right? So we're following across. So I to the power of 5, then plus I to the power of 3. Now we're going to do this one. So -5i times I cubed is going to be -5i to the power of 4. And -5i times I is going to be just -5i squared. So we're going to get that equation. Now, I is just equivalent to I squared, we talked about how that's the basis of everything. It's just -1. Now, I cubed is going to just be equivalent to I squared times I, right? So it's going to give us -I. And then I to the power of 4 is essentially just I squared. And -1 squared is just 1. And we can kind of always use it from there. So we can kind of build a basis. So if we have I to the power of 2n, right? That's going to be just equivalent to -1, right? If we have I to the power of 3n, that's going to be equivalent to -in. So in. If we have I to the power of 4n, that's going to just be equivalent to in. 1n. Let me just rub that out so it's a bit cleaner. So what we get from this is I to the power of 2n, or is just equivalent to 1 to the power of n. If we have this, we have negative I to the power of n. If we have this, it's going to just be equivalent to 1 to the power of n, right? So if we had I to the power of 8, it would just be I to the power of, I to the power of 2, and then just square it again. So I to the power of 4 squared, which is just 1, right? Still 1. But in all, these are kind of the rules that we can use. So whenever we have this, we kind of try and decompose it so it's in terms of one of these, right? So what I to the power of 5, we can change that to I to the power of 4 times I, right? I to the power of 3, we already know what that is. It's going to be negative I. 5I to the power of 4, we know what I to the power of 4 is. It's just 1. And I squared, we also know what that is. It's just going to be negative 1, right? So what we're going to get here is I to the power of 4 is negative I. And then we get negative I here. Sorry, positive I, not negative I. Positive I, right? Because the I to the power of 4 is just I. And then, I to the power of 4 times I is just I. And then we get plus I, minus 5, plus 5. So all in all, we can see everything cancels out, and we're just going to get 0. So that is my expand and simplifying. So it all simplifies to 0 here. Alright. So then we realize the fractions. So realizing fractions is kind of like rationalizing a surd. So you know how when you try and rationalize a surd, you have something like, I don't know, root 2 plus 3 over 1 minus root 2, and they want you to rationalize it. So what you can do is you can go root 3 plus 1 minus root 2, and you can times that top part by the conjugate of it. So you get that, and you can kind of times it across, and you'll just get that it's going to be root 2 plus root 2 squared, so that's 2 plus 3 root 2, right? And that's going to be all over I squared minus root 2 squared. So we'll essentially get that this is going to be 2 plus, so that's going to be 4 root 2 plus 5. So we'll get 5 plus 4 root 2, and that will be 2 squared, right? So we'll just get that's all over negative 1, so we'll get a negative version of that, right? So that's what it's going to be equivalent to. It's the exact same thing as what we're doing here. So when we have I plus 3 over 2I minus 1, we times it by something called the conjugate of it. Now, the conjugate of it, if we have x plus iy equals to z, the conjugate of that is now going to be x minus iy, right? So it's just changing the imaginary component, negating that. So we can times that by 2i. Yeah, we can times it by 2i plus 1 as well. Well, maybe let's not do that. I mean, it still is possible, right? But I guess by convention, we can just talk about times by its conjugate. Because even with 2i plus 1, it should still give you the same result. The real thing is that we need a difference of products of some sort. So it's going to be negative 1 plus 2i, negative 1 minus 2i over negative 1 minus 2i. So it's entirely possible just to also times this by 2i plus 1 as well, because it would give you the same result, because the main thing is that you just don't want any remaining i's at the bottom. But let's just do it this way for convention's sake. So when we times that across, we'll get this as I plus 3 times negative 1 minus 2i, and that's going to be all over negative 1 squared minus 2i squared, right? So when we kind of put that across, we'll get that this top part is going to be negative I minus 2i squared minus 3 minus 6i, right? So we can kind of get that, and then this will be all over 1 minus 4i squared, so i.e. 1 plus 4, because remember this cancels out to negative 1. So we'll get that if we kind of group like terms here, and remember I squared equals to negative 1, so we'll just get that it's going to be negative I plus 2 minus 3 minus 6i over 1 plus 4. So we can group everything now, so we'll just get that this is going to be negative 1 minus 7i over 5. And that's going to be our overall answer. So it's essentially just doing what we normally do with surds anyway, and just rationalizing it using that. Cool. Alright, so let's talk about solving. So just like how we solve for normal quadratic equations and solve for normal polynomials, we can kind of apply the same methods here. Evidently this, right, the discriminant is smaller than 0 because we essentially just have 0 squared minus 4, 1, 64, which is evidently going to be smaller than 0. So this is why it says solve over C. So if it doesn't say solve over C, so we really need to keep our eyes peeled for whether something says solve over C or not solve over C. Because if it says just solve over, like x belongs to R or something like that, then we wouldn't be, even though we might know about complex numbers and we know how to utilize them and all that kind of stuff, we're still not going to use them because they're asking for only real answers. Now, if they asked for complex numbers, like in this question, an important thing to do is solve for the complex ones. So what we can do is utilize our knowledge and kind of introduce that there. So instead of writing x squared plus 64, what we're going to write is x squared minus 64 I squared, and that equals to 0. So now that we have it in this form, we can apply the DOPS thing of a squared minus b squared is equivalent just to a minus b, a plus b, right? So what we can go here is x minus I, x plus I is equivalent to 0. So therefore we will get that x will equal to 8i or x will equal to negative 8i as our solutions. And that one, that's just how you do it. That's all you need to do. So just make sure that they're asking you to solve over complex numbers rather than just the real numbers. Okay, amazing. So let's kind of extend that further to doing something like this where it's a little bit more less straightforward. So once again, we just check the discriminant quickly. So once again, b squared minus 4ac. So it's going to be 2 squared minus 4, 1, 5, which is going to be equivalent to 4 minus 20, which is negative 16. So that's smaller than 0, so we're unhappy with that, so we can't solve for real numbers. But we can try for complex numbers. Now, the question is, where do we introduce our I squared? And we're going to use our smart little noggins and know that we can actually change this into another form where we normally actually do the DOPS products from, right? There is not really a way that we can factorize it straight, unfortunately, so we have to just use a bit of our DOPS products and do a special process called complete the square, which you all will be quite familiar with from doing in polynomials and doing it in methods as well. So when we try and complete the square, what we try and do is we look at the x term, we half it, so 1, and square it, so 1 squared, and then we minus as well, right? Because we can't just add random things. We need to actually make sure that we're compensating for it. And then we can plus 5 at the end because we're not changing that. So that's equivalent to 0. Right. So then we grab the first 3 terms because now that's the perfect square. So we'll have x plus 1 squared plus 4 is equal to 0. Now, once again, we can see if we put this to the other side, it would be negative, right? So we'd have x plus 1 squared equals to negative 4. So what we're going to do here now is essentially when we have this negative 4, we can now change it to 4i squared, okay? So we're going to have x plus 1 squared equals to 4i squared, right? So therefore we can kind of have a look here, and now that we have this 4i squared instead of this negative 4 on the other side, we can actually solve for this. So we'll have x plus 1 squared here, and essentially we can now try and plus or minus it, right? So we'll have x plus 1 will equal to the plus or minus of root of 4i squared. Now 4 can be rooted to 2 and I squared can just be rooted to 1. So we'll have x plus 1 equals to 2i, right? Plus or minus 2i. So we'll have that x will equal to negative 1 plus or minus 2i. And this is where sneaky, something called the conjugate root theorem kind of sneaks in. So what the conjugate root theorem is that if we have something like ax squared plus bx plus c, and this applies for any polynomial, not just when we're considering quadratics, it applies for any polynomial in the universe. If a, b, c all belong to R, and we're solving over a complex plane, if there is one complex root, there must be another complex root, right? And that's just to compensate, because if you don't have two complex roots, you'll never be able to return to real coefficients. So that's why, in order to compensate for that, the roots must be conjugates of each other. So that just means that if you have a root -1 minus 2i, and they've told you that, and you can see that they're all real coefficients, our other root must be -1 plus 2i. Cool. Alright, so let's keep on going with this. So we now have x squared plus 2a equals to 0. So what we can do here is now we'll do the same thing. We don't really know what 2a is, but that's okay. Yeah, we assume that a is probably bigger than 0, so that's why it doesn't really matter what a is, right? Or if this was a negative, then if a was a negative number, technically you wouldn't really need to do complex, but we're assuming a is bigger than 0. Otherwise, why would they be asking us to solve a complex? So we can change this to x squared minus 2i squared equals to 0. So once again, we can factorize it into the two forms. So x squared minus root 2a squared, x plus our root 2ai squared. So essentially we're going to get x minus 2i 2a and x plus I 2a. Note, in terms of kind of solving and doing stuff with your complex numbers, your I should never really be left in an equation, so it shouldn't really be left as a squared cube like we saw before. We can simplify it further. It also shouldn't be left under square roots as well. So if you find that you can't get your I out of the square root or something, just, sometimes it is like that, but it's kind of quite rare. So if that does happen, just be a bit careful and just make sure to recheck your working out to make sure it looks like everything looks reasonable. Okay, so that was the Cartesian form that we were playing with a little bit, and there's another form called the polar form. So where the Cartesian form is kind of talking about coordinates, where we're talking about longitude and latitude, the polar form is talking about how far we're going and what angle we're going. So it's kind of like going 30 degrees to the north for 400 meters. That's essentially what a polar form is telling you. It's telling you how far to go and what the direction is to go. Whereas the Cartesian plane is kind of pinpointing where the position is. So we also represent it via this thing called the Argand diagram. So whereas we have the Cartesian plane for real numbers, we have something called the Argand diagram for complex numbers in general, and we just replace the axes with real component, imaginary component, because it's x plus iy in terms of z. So our x kind of corresponds to our real component, and our imaginary component kind of corresponds to our y. So that's how we can kind of represent it. And what we do is we represent it as r cis theta. So r will tell you how far it is from the center, and cis theta will tell you the direction where it's going in. So theta will tell you the direction, and it's always measured anti-clockwise from x-axis, and hopefully it will ring a little bit of bells in terms of why it is like that. And why it is like that is because, remember, for our circular functions and all that stuff that we're working with, because complex numbers, the polar form is kind of represented from circular functions as we can use so that it's transferable across, I guess. It's done in the same way, because in terms of circular functions, it's always measured anti-clockwise from the positive direction of the x-axis. In our equation that we have here, it's also, in our complex numbers that we have here, it's also measured from anti-clockwise from the positive x direction. Cool. Alright, so then that kind of represents that. The next part is our absolute value, otherwise known, it can also be represented like this. So it might seem a bit familiar from when we're doing modulus functions or absolute value functions. So that's our r component, and it's just a squared plus b squared. Hopefully this also rings some bells, because if we know this is a plus bi, we can see there a, b, Pythag it, so you have a squared plus b squared, and then root it to get the third side. Okay, so essentially from our knowledge of angles, we know that theta equals to 2 pi k, right? For if we have just a normal, like without any like changes in the period, it's going to repeat every 2 pi k. Now, because if we said we were repeating at 2 pi k, so if we go back to here, right, and we talk about r cis theta, there would be thousands of angles which would represent the same direction, right? Because of the repeating periods that we have for circular functions. So rather than doing that, because mathematicians hate when we have multiple answers for the same thing, we have to give them a range of values which there's no repeating, right? Arbitrarily, they kind of just chose negative pi to theta, negative pi to pi, and it's important to note that it's the pi which is included rather than the negative pi. So if you get a solution which is negative pi, you need to make sure to exclude that one as well. So your arguments in terms of your solutions and everything, it must be within this domain. Sometimes they'll ask for a lowercase arg in which you might get away with being outside the domain. But I would say it's always safest to try and keep your answers within this domain, and this can be represented by the capital. So the capital versus the lowercase, the capital actually refers to this domain for the angle, whereas the lowercase doesn't. But I would just be really careful, because especially when you're solving, you'll always be solving for this domain. Okay. In terms of multiplication and division, so previously we would have done, kind of how we did a bit of expansion, we did the FOIL, it was okay, but like it can get pretty complicated evidently. So imagine if you had something like root 3 plus 4i times 17, or not 17, like 7 over 2i plus 5 over 2, and like imagine if you had to do that, it would be okay, it would be doable, but it would just be a bit gross to do, right? So our alternative to make that less gross to do is to use a polar number. So how we can use our polar number is essentially we'll have z1 times z2 will give us r1 r2 times our cis1 minus our cis2. So this should be cis1 plus our cis2. So we add the angles and we multiply those, and when we divide the r components, so we divide the modulus and minus the angles. So one thing that's really important to kind of note is that like these formulas, right? We look at them and we're like, yep, they look okay, they look reasonable, yeah? Where do they actually come from? So where do they come from will be only answered when you learn about all the different circular function theorems and stuff like that. So once you are able to have a bit of a chat about that and understand the circular function theorems, particularly the addition of angles, I would encourage you to revisit these concepts and try to actually prove these, because they have been known to be questions from VCA and things in the past. So I would recommend maybe coming back to it and just making sure you know how to prove these relations. Cool. Alright, so let's talk about first converting things to polar. So if we try to convert things to polar, the first thing that we want to do, I like to do it this way, where we kind of like break it up into segments. So when we try and break it up into segments, what we'll have is that we'll have the r component and we'll have the theta component, right? So what we can have here is the r component. Remember, we said that's just the modulus of z, which is otherwise known as a squared plus b squared. So in terms of our polar number, remember it's I, so it's going to be 1, this is going to be I. So we can kind of say, oh, okay, so it's going to be approximately there. So we can kind of see that it's just going to be root 1 squared plus 1 squared, which is going to just be root 2. All right, so then our theta. Our theta is best found via going tan inverse of our y over our x component. So tan inverse of that, we'll be thinking 1 over 1, so it will be tan inverse of 1. Now, the only catch is that we need to tell them which quadrant it's in. Because remember, for any angle that we find, tan, it could be in, so for positive ones, it could be in this quadrant, or in this quadrant, if we're talking about negative things. So how would we be able to predict this? And the answer is, we kind of just look back to the equation that we're trying to convert, right? So it's 1 plus I, which means that both of these are positive, right? So that means x is greater than 0 and y is greater than 0. So what that tells us is that it must be in this quadrant right here. So therefore, we're going to just be using the first angle, and we think, okay, when does tan equal to 1? And we think, okay, that's when we have 1 root 2, otherwise known as the pi and 4 triangle. So we know that theta will therefore equal to pi and 4. So then we kind of collate that all together, and we'll say 1 plus I, and we put that together, so it's root 2 cis pi on 4. And by the way, the expression of cis, because people are often a bit curious about where cis comes from, or there's nothing explaining here, so I'll just write it out on this slide. Cis actually just represents root 2 cos pi and 4 plus I sine, what did I just do? I sine pi on 4, and it's this part and this part, which is the cis, so it's kind of like an abbreviation of it, essentially. Right, okay, so let's try and convert this one to polar now. So once again, we start off by breaking apart into two parts. So we break it apart into the r component and the theta component. So the r will equal to root of -3 squared plus 3 squared, which is going to give us 3 plus 9, which gives us 12. So that's going to just be 2 root 3. And that's going to be our root that we're talking about. Alright, so then what we're going to do is we're going to try and find the other part of it now. So tan inverse of 3 over negative root 3, that's going to give us that's the tan inverse of negative root 3. We think of when tan is equivalent to negative root 3 and build up our triangle. So now we want the root 3, 1, 2 triangle, and it's opposite over adjacent, so we must be looking at this angle up here, so pi on 3. So therefore, we're going to be considering this as our pi on 3 angle. But remember, we look at the quadrant. This is negative. That means it's either in this quadrant or this quadrant. We look at our components. X is smaller than 0. Y is bigger than 0. So therefore, it must be in this one right here. So therefore, we're going to say, so our base angle that we want is pi on 3. And it's in the second quad, right? So it's going to be pi minus pi on 3, otherwise known as 2 pi on 3. Okay, cool. So then once again, we piece it all together. We get negative root 3 plus 3i will equal to 2 root 3 cis 2 pi on 3. Okie dokie, amazing. Alright, so let's get moving on again. So next we want to convert negative 13. So like I said, all real numbers are complex numbers. So even if you don't have an imaginary component, you can still consider it a complex number because you're still able to convert it into the different forms. Like this is essentially just 13 plus I, like plus 0i, right? And there's not really much difference compared to that. Cool, awesome. So then therefore, what we can do here is we can kind of look into this one. So once again, we can split it into the real and the r, so the modulus, and also the theta part of it. So what we can do is we can kind of split this up, and we'll say that this is going to be r is going to equal to the modulus of z, which is equal to root a plus b, and we know that it's kind of on the axis actually instead. So it's actually right here. That's where, oopsies, no, not there. Right there. That's where probably the angle is. That's probably where the polar number is. Ignore that. I'm going to rub that out so that we don't get confused. So it's actually right there. That's where we're looking at. Okay, so therefore we can write this as root negative 13 squared plus 0 squared. So it's just going to be 13. And then we can talk about theta. So theta is tan inverse of 0 over negative 13. So that's going to be tan inverse of 0. And we think to ourselves, okay, when does tan equal to 0 in terms of our unit circle? So, and in terms of just things in general. So that will mean that the sine equals to 0, so it must be along this axis, and that the sine equals to 0, so that must mean that it's along this axis. So it could either be here or it could either be here, right? Then, once again, we look back into our equation. So we note that the x part is negative. So that must mean that it's on this side of the thing. So if we kind of do a bit of a cross section, we notice that it must be here rather than the one here, because x should be positive on that one. So we know that now, therefore, we would have pi as the angle. So when we write this out, this is going to just be equivalent to 13 cis pi. And look, it looks so much more complicated written like this compared to this, but it's just one difference of writing it into polar form. Alrighty, okay. So now let's talk about going in the other direction, and I think that the other direction is actually a bit simpler because you don't really need to break it up. You can kind of just do it a bit straight, and it kind of goes sequentially down rather than having to break it apart and then put it back together. So what we can do here is we essentially just rewrite this as -4 cos 2 pi on 3 plus I sine 2 pi on 3. And then what we're going to get here is that it's going to be -4, right? And then once again, we have to check our angle. So our base angle that we're working with is pi on 3, which is this angle here. Remember, our triangle is √3, 2, 1, because it's hwachad out of a 2, 2, 2 triangle. So we know that it's going to be, so in terms of our cos, it's going to be 1 over 2, right? Because we can see that it's adjacent over hypotenuse. So it's going to be 1 over 2. And then our sine, so plus I, our sine is going to be √3 on 2, because we can see opposite over hypotenuse. So √3 on 2. Okay, the second part of this is we once again need to consider what quadrant we're working in. So 2 pi on 3 is going to be in the second quadrant, and we can see y, or the imaginary component, is going to be bigger than 0, but the real component of z is going to be smaller than 0. So this part should be negative, so we'll get -1/2, and we'll just get positive version of this, right? Okay, so then we kind of simplify it and make sure it looks nice. So we'll get -4, -1/2, √3, sorry, this is just times. That looks like a plus instead, √3 on I. And then we can times the 4 out as well. So we'll just get 2 minus 2 √3i. And that's our Cartesian form. Cool. Alright, so we can kind of repeat the same here, except for our, now it's square root 2. So once again, we expand everything out. We get square root 2 cos 3 pi on 4 plus I sine 3 pi on 4. And this time we can check, maybe do the check before, so it's a bit neater. So once again, 3 pi on 4 is in this quadrant. We do our triangle for pi on 4. So that's 1, 1, √2. And we can see it's 1 over √2 and 1 over √2. Or alternatively, so it's 1 over √2. Or you can write it as √2 over 2, which might be preferable here, given that, like, we can check which one's preferable. If there was a 2 on the outside, I might go with this one. But because there's a √2 on the outside, I might actually go with this one, so it cancels out. Once again, we see that cos is negative, so we're going to have √2 times -1 over √2. And sine is positive, so we're going to have plus I over √2. And then we can kind of times the √2 out. So we'll just get this as -1 plus I. And it's completed. So we can kind of tell which quadrant it is by which one's positive and which one's negative. And either back or forth, you can kind of always tell what quadrant a complex number is going to lie in. And like, even if we were doing this via a Cartesian form, so this should be -1, 1, you can kind of see what quadrant it is when you try and graph it out as well. Okay, so now that we've talked about how to convert polar to Cartesian and Cartesian to polar, let's now chat about actually doing it and doing this complex multiplication. So essentially, it's always easier in polar, and I want you all to remember that. Even if like you have to convert to polar and then convert back, I'd still recommend it, because I just find it's so much easier and just so much cleaner as well, because the more you do, the more you are prone to making mistakes. So I just find if you convert it once and then do all the stuff and then convert it back, it's often a lot nicer. Okay, so Z1, Z2 is going to be equivalent to R1, R2 cos theta 1 plus theta 2. So what we're going to do, so z1, z2 here is 7 times 6. Cos theta is going to be pi on 3 plus pi on 2. Now, the real trick here is that this, right, because this is 3 pi on 6, and this part is 2 pi on 6, right? So this all stays under our equation. But, for example, if we had 2 pi on 3 plus pi on 2, you would note that that's going to be outside, because our domain goes from here to here, right? And then here to here, yeah? And it doesn't include that point at the end. So if this was 2 pi and 3, instead of just pi and 3, we would actually need to exclude a value at the end. So we would have to go backwards. So if this was 2 pi and 3 plus pi and 2, we would have to find the angle and add the angle up, and then we would have to find the corresponding angle in the domain of this domain, right? Because we want our capital R. But for this one, it's not much of an issue, so we can just say that's 42, cos this is 2 pi on 6, and this is plus 3 pi on 6. So we'll get that this is going to be equivalent to 42 cos 5 pi on 6. And sometimes they'll get you to convert it back into a Cartesian form, and if that's the case, once again, we can kind of figure out the quadrant. So once again, it's going to be in this quadrant, and for now we're looking at pi on 6. We're going to use our root 3, 2, 1 triangle, and then we're going to just get that's going to be 42 on the outside. Our cos 5 pi on 6 plus our I sine 5 pi on 6, and we'll get that this is going to be equivalent to 42. Our cos 5 pi on 6 is going to be equivalent to root 3 on 2, right? And it's going to be negative since the quadrant, root 3 on 2. And our sine is going to be positive, and it's going to just be a half. So plus a half I. And then if we kind of expand that out, it's going to be negative 21 root 3 plus 21I. Cool. Awesome. All right, so let's talk about dividing those two now. So it's z1 divided by z2. So we're going to have, remember we know that that's going to be r1 over r2 cis theta 1 minus theta 2. Now what we're going to do is just put that all in. So if we have z1 over z2, what that's going to be equivalent is r1, so x, so 7 over 6, right? So cis therefore will be pi on 3 minus pi on 2, and we'll get that this is going to be 7 over 6 cis of, so that's 2 pi on 6, 2 pi on 6 minus 3 pi on 6, so we'll get that this is going to be 7 over 6 cis negative pi on 6. And once again, if we wanted to kind of convert to polar again here, we could make this 7 pi on 6, and we could kind of expand that out. So it would be cos negative pi on 6 plus I sine negative pi on 6. So think of the quadrant, negative pi on 6 is here. Think of the triangle, once again, it's the root 3, 1, 2 triangle for pi on 6. So we're going to write this out as, now our cos is positive, so 7 over 6 is going to be 1, it's going to be root 3 on 2, and our sine is going to be a half, so it's going to be negative a half though, because of the quadrant. So then if we kind of expand that out, we would get that this is going to be 7 root 3 over 12 minus 7 over 12i. Cool. Awesome. Alright, so let's now try the other way around. So now we want r2 over r1 cis theta 2 minus theta 1. And it's important to know which one's which, right? Because for our multiplication, it doesn't really matter which one's which. But for division, it does, because 1 divided by the other and the other divided by the 1, it's not going to be the same thing, right? It's kind of like 5 over 4 is not the same as 4 over 5. So that's why we need to just be a little bit more careful. But 4 times 5 and 5 times 4 is going to be the same thing. So therefore what we can do is, therefore we can write this out. So we'll have this is going to be 6 over 7 cis of pi on 2 minus pi on 3, which will give us 6 on 7 cis 3 pi on 6 minus 2 pi on 6, which is going to be equivalent to 6 over 7 cis pi on 6. Once again, we can do our conversion to, so this is only if they ask you to convert to Cartesian, otherwise you can just leave it, but I thought, might as well take the extra step so we can go through it together. So now it's in the first quadrant, and in terms of our triangle, once again, it's the pi on 6 one. So our color and the angle, I'm going for root 3, 1, 2. So we'll know that that's going to be 6 on 7 cos of pi on 6 plus I sine pi on 6. And that's going to be 6 on 7. Therefore, pi on 6 is going to be root 3 on 2. And our pi on 6 here will just be a half. And it's going to be positive because it's just the first quadrant. So therefore, we can kind of expand that out. So we'll get 6 root 3 over 14 plus 1 over, 6 over 14i. And we can kind of simplify that down a little bit more. So we get 3 root 3 over 7 plus 3 over 7i. And we probably could have cancelled out the 3 up there as well. But it's fine either way. Just make sure to cancel it. Okie dokie. Alright. So now let's talk about our Z2 cubed. Okay? And this is introducing something called de Moivre's theorem, which is not really a part of the 1-2 study design, but it's something that you can kind of notice if you want to. Essentially what it is that if z equals to r cis theta, remember that z1 times z2 was r1, r2 cos theta 1 plus theta 2. So therefore, if we had z1 times z1, we would have r1 squared cos theta 1 plus theta 1, right? And if we kind of repeated that again and cubed it, we would end up with r1 cubed cos theta 1 plus theta 2 plus theta 3. And repeat it after and after. So therefore, we kind of get the conclusion that z to the power of n would just equal to r to the power of n, cis and theta. And that's what de Moivre's theorem is. But essentially, we can really, it's just a formula which is derived from the multiplication rule that we've already done so far. So if you do see it, you can always try and use it. But if you don't, I don't really think it's too much of an issue, especially in 1-2, but you'll definitely be doing a lot more of it in 3-4. I don't really think that you'll be solving much using this, but I think you might be using it just to kind of expand numbers like this. So it wants z to the power of 2 cubed, which means that we need z2 times z2 times z2. So we'll do it without just do it by multiplication first. So what that means is we'll have r2, 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 and we'll have cis theta 2 plus theta 2 plus theta 2, right? So what that will mean is we'll have 6 times 6 times 6 and cis 3 pi on 2. So that's going to be 216 cis 3 pi on 2. And importantly, beep beep, we see here that it's outside of here because it's here. So instead of writing it as 3 pi on 2, we're going to write it as cis negative pi on 2, right? And then after we kind of do that, you can also, if you wanted to convert this one to polar, it's relatively simple enough. This should just be negative 16i, because we can see that it should just fall exactly on the y-axis. Okay, so let's have a go at this one now. So what it's asking us to do is that if z plus I 1 over z belongs to r, we have to show that the modulus of z equals to 1. Okay, so let's name z equivalent to 1 plus bi, and therefore we can say that this is a plus bi plus 1 over a plus bi. Now the easiest thing to do here is try and rationalize this. So a plus bi will be equivalent to a minus bi over a squared minus b squared I squared, right? So this will give us a plus bi plus a minus bi over our a squared plus our b squared, right? Cool. So if we need this to be equivalent, right, therefore we can also apply, so if we do it this way, we can kind of see that therefore this thing would need to be like this top thing, so a minus bi would need to be rational, and this part would also need to be rational as well. And there's also another way of kind of approaching this. So So there's kind of two ways to approach this. So if we kind of do this where we make everything at the top. So if we now go a plus a squared plus b squared, sorry, and then plus a minus bi, we'll eventually get that when we try and transfer that across. So the a parts shouldn't matter too much, but we'll get la squared bi plus b cubed I minus bi, and then we'll have the kind of the real components as well. So we'll have like a cubed plus a b squared plus a. But this is the part we're interested about, right? Because if this needs to belong to real, that means that a squared bi plus b cubed I minus bi must equal to 0, right? So we can kind of factorize that in terms of b in terms of b and I. So if we try to do that, we can say that, all right, so therefore if we factorize out b, we'll get this as a squared I plus b squared I minus I, and that equals to 0, right? So therefore you'll get that you'll get that b equals to 0, or b will be equal to, so if we kind of put that across, well, we don't need the i's anymore. Just remove those because we're trying to say that it's equivalent to 0. Yeah, so this is equivalent to 0, so if we kind of just remove the i's because we're trying to say that this thing is equivalent to 0, just to make our life a bit easier. It's not strictly necessary, but it just means that we have less things to work with. So b a squared and then b squared minus b, minus 1. Okay, so that would mean that we have b squared would equal to 1 minus a squared, right? So therefore b would equal to the root of 1 minus a squared, right? So a plus or minus. So therefore we kind of can get that relationship as well. I guess the only concern with that is that if we have b equaling to the plus or minus root of 1 minus a squared, that would mean that a at most, right? So those are the two types of situations we can have. So in order for this to happen, we need b. So if b is equal to 0, that would mean that z is just simply equal to a, right? Whatever a is equivalent to. And if we look into here, right, because if b is equal to 0, that means you wouldn't really have, like you would have a complex number, but it's kind of a specific case, right? Like that's when it just literally equals to a real number. So 1 over like a real number plus 1 over a real number is always going to be a real number. It's not terribly exciting, right? But when we look at this side of it, so if we want this to also work simultaneously, what we can have here is that we know that 1 minus a squared has to be bigger than 0, right, in order for b to still be defined. So therefore a squared has to be smaller than 1. So we can kind of talk about this, well, smaller or equal to 1 can be, if we can kind of fuse it with that. And for that to be a thing, we can kind of draw out our little equation there, right? So from there, what we can kind of conclude from there is that we'll have a squared in order for b to actually be equivalent to 0, in order for like this to have no b component, it actually needs to be exactly at the graph. So technically we could say a is 1 or negative 1 in order for them to be equivalent, but otherwise we can also make this like just underneath the graph as well, right? And if we make that part underneath the graph, so let's say it's like 1/2 and positive 1/2, so in any universe, like if this was a half or positive 1/2, so let's say that's 1/2, right? Let's say a equal to 1/2 instead, we would get that this would be equivalent to just a equals to 1/2, so therefore we would have that b would be equivalent to root 3 of that, so 1/2 of that is 1/4, and then 1/4, so 3 on 4, so we'll have root 3 on 2, right? And then you notice like when you kind of put those two together, it will always be equivalent to that, because like when they add together, it will always give you the same number, right? Because essentially root 1 minus a squared all squared plus a squared is always going to just equal to 1, regardless of the universe. let's talk about the other way of looking at this as well, just, for interest more than anything. So another way that we can look at this is that we can say a plus bi plus 1 over a plus bi, and then we can also say a plus bi all squared, right, over a plus bi has to equal to, or just is a thing, right, is belonging to z. So what that means is that we'll have this as a squared plus 2ab plus bi squared, right, over a plus bi, and then we kind of end up with the same thing, so we can have a squared minus b squared plus 2abi, and then we'll say that's all over abi, right? And in order for this to be real, we have to rationalize the bottom part first, and then we can go a squared minus b squared plus 2abi, and then times by a minus bi, and that will once again be over a squared plus b squared, and then you can kind of get the same thing as what we were doing before by doing a different method this way. It's always good to know different methods to do things. Okay, awesome. So that concludes our complex numbers. Now let's jump into talking about series and sequences. So series and sequences is essentially series is talking about the sum of a sequence, and the sequence is just an ordered list of numbers. So 1, 2, 3, 4, 5, 2, 4, 6, 8, it can be really anything. In Specialist, we talk about two different types of sequences. So we talk about arithmetic sequences and geometric sequences. Arithmetic sequences are to do with adding, and geometric sequences are to do with multiplication. So how do these sequences work? So first of all, let's talk about arithmetic sequences. So arithmetic sequences are essentially when the successive terms involved adding something. So we're adding d on each time. So we're going 2, 4, 6, 8, so that we're adding 2 each time. Or if we're going 1, 5, 9, we're adding 4 each time. Or if we're going 1, 5, 9, not 1, 4, 9. If we're going 1, 7, 13, or something like that, we're adding 6, yeah? Like, we can add different terms each time. And the d thing will be the thing that's changing. And our tn minus 1 is going to be how we represent it. Importantly here, we need to tell them what term we started on in terms of the recurrence relation, just because if we don't tell them what term we actually start on for here, we don't really have any term to start on. So we always need to tell them what a is, and a is the first number in the sequence, or we need to tell them what t1 is, essentially. Okay, so if we write, so this is called a reoccurrence relation, and this is called the rule, right? So if we want the rule so that we're able to kind of pinpoint exactly, so if we wanted to be able to find the fifth term straight away, we would need to find a rule for it rather than doing this, because if we wanted to find the fifth term using this, we'd need to find the fourth term, and then the third term, and the second term, and then kind of going backwards, right? So because we are not very keen on doing that, we can just use this instead to find the sequence, and essentially it's just a rearrangement of the letters and the rearrangement of the terms here to kind of form this. And A represents the first term in the sequence, so it represents your T1. And D is that common difference, so 2, 4, 6, whatever. So the difference in that sequence would have been 2. Cool. So if we want to find the 12th term of this sequence, so the first thing that we want to do is figure out a rule for this, right? So we want to compare what's happening in between each of these. So we note that it's adding 4 on 4, or adding 1 essentially. So 4 on 4, 4 on 4. So therefore we can derive that d equals to 1. A would equal to negative 1/4, right? So therefore our Tn would be equal to a plus 1n minus 1d, which is our equation for it, and we just plug everything in. So we get 1/4 plus n minus 1, which is n minus 1 still, times by 1. So we'll end up with 1/4 plus n minus 1, so we'll get that this is negative 5/4 plus n. And we can try for different n values. So for the first n value, that would equal to 1, equals to 1/4, looks good. N equals to 2, 2 plus 5 on 4 is going to be 3 on 4, looks good. 3 plus 5 on 4 is 12 on 4 minus 5 on 4, so that's going to be 7 on 4, like here. So we're happy with that as well. Alright, so then we can kind of now that we're happy with the actual sequence, so it's always good to double check throughout what you're doing. So now that we're happy that we've double checked and looked and made sure our rule is correct, what we can do next is actually sub in. So now we're looking for n12, so that's going to be negative 5 on 4 for us plus 12. So negative 5 on 4, and we can convert that into fourths as well, so that's 48 on 4. So we'll get that 43 on 4 is equal to 12. So therefore 12th term is 43 on 4. Cool. Alright, next one. So this is kind of a bit of a reverse one because they've given you the terms, but they've only given you really specific terms, right? But once again, we know that Tn equals to a plus n minus 1d. And once again, we can try and sub those in. So there's kind of two ways of going about this, and one of the ways is just finding the common difference first. You can either do simultaneous equations from the get-go, or you can just use like the common difference. So if we look at these two terms, right, if we go 62 minus 22, that's going to be 40, and that's going to equal to d times by 15 minus 5, right? That's going to equal to 40 because that's the difference of how many terms. So we'll get that 10d will equal to 40, and therefore d will equal to 4. So we can sub in here that a plus n minus 1 times 4 is what's going to actually give us the value, right? Okay, cool. So therefore we can now try and find what this is, and we can sub in either one of them. So let's talk about t to the power t to 5. So that will be a plus 5 minus 1 times 4. And that's equivalent to 22. So 22 is equal to a plus 4 times 4, so 16. So a for us should be equivalent just to, so that should be equivalent to 6, right? Okay, so therefore we can get the equation Tn will equal to 6 plus n minus 1 times 4. So we'll get that this is going to be 6 plus 4n minus 4. So we'll get that this is going to be 4n plus 2. And we can kind of check here as well. So if we times 15 by 4, we'll get that that's 60 plus 2 should be 62. Alright, so let's find T100. So T100 is going to be 4 times 100 plus 2. So we'll end up, that's going to be 4. It's going to end up becoming 402. Alright. Okay, so if we have an arithmetic sequence which goes like this, so i.e. we have a, then 2a, then a squared, right? So we have this and this and this. So we know that the difference between these two is a, and the difference between these two should still be a, right? So therefore we can say a squared minus 2a is actually going to be equivalent to a. So that's because we know that the difference should be there. So a squared minus 3a is going to be equal to 0. So therefore we'll get that a minus 3 will equal to 0. So therefore a will equal to 0, or a will equal to 3. But a cannot be equal to 0, because if a is equal to 0, you're not really going to have an arithmetic sequence, right? As a is common difference. So therefore a will equal to 3. And we can kind of see that. So we have 3, 6, 9. And that's why a squared and a. Okay, let's talk about a bit about geometric sequences now. So geometric sequences is the other half of sequences that we chat about. So essentially a geometric sequence is, instead of us plussing on terms each time, what we're doing is now we're kind of timesing the terms each time, right? So instead of doing the plussing, we're timesing instead. So now instead of having, we're going to have Tn equals to r Tn minus 1, so as in we're timesing the previous term by something to get the next term. Once again, it's more useful to have the rule for it, because that means we can just we can say we want T100, we want T50, we can tell what that number is straight away. So once again, we'll have the first term, because we need to know where we're starting, so we need a first term, so a, and then we have r, which represents the common ratio, so how much I need to times by each time. Cool, so let's chat about that. So now we have to figure out what's going on from here to here to here to here. So we can figure out that that's actually timesing by root 2 and timesing by root 2. So therefore we can kind of identify that we'll have r will equal to root 2 and a will equal to root 3, right? So that we're going to apply this to our formula. So Tn equaled to our a times our n minus 1. So that's going to give us root 3, root 2, n minus 1, right? So you can you can expand this further if you wanted to, but I feel like it's not really worth it. You can kind of just leave it like that if you want. And we can just make sure to check. So if we subbed in 1 minus 1 is 0. That should just be 1. That looks good. If we have 2 minus 1, so it's root 3 times root 2, so that's root 6. Looks good. If we had 3 minus 1, so that's root 2 squared, so we'll have 2 root 3. So it looks good. So we've done our checks, and now we can move on to actually subbing it in. So we'll have root 3 times root 2, 12 minus 1, which means we'll have root 3 of 2 to the power of a half times 11. So we'll have root 3, 2 to the power of 11 on 2. So therefore we'll have root 3, 2 to the power of 5 times 2 to the power of a half. Okay, so why I did it that way is because I find this will be easier for us to actually write out at the end. So the last one will be left over, so we know that we'll have a root 6, and then 2 to the power of 5 is 32. So essentially we can write T12 is equal to 32 root 6. Okay, cool. So once again, they've given us rules instead of what we're they've given us just 2 separate terms to work with. So we know that Tn equals to ARn minus 1. So for this one, we can try the simultaneous equation method, since we talked about the common, talking about dividing or timesing by the common difference in the previous one. So, or more like we talked about the common thing that we're doing, we did it with the common difference and worked it out by there. And for this one, you could do it via a common ratio just by dividing the two and then making that equivalent once again. But, we should try different methods for things just to display it. So if we sub in T10, that's going to give us A times R to the power of 9, right? And that's 512 is going to be equivalent to A R to the power of 9. If we sub in T15, that's going to be A R to the power of 14. So we'll get that 13684 is equivalent to A R to the power of 14. Now, we have equation 1 and equation 2, and what we can do is just try to get rid of the A's. So we can try and divide 1 by 2. So, 2 by 1, sorry. So that the bigger number is divided by the small number. We'll get 512. This is equivalent to just the A's cancel out, and we'll have R14 over R9. Okay, so if we look into this, we can try and figure out how many times this goes in. I'm predicting this will go into 3 times, because I can see if I times this by 3, it would be 15 something. So I'm going to try that. So 15 times 3, so I'll get 6 here, I'll get 3 here, and then I'll get 15 here. So that's not quite as big as I need. We can also do a bit of just long division. You can either decompose it or just do a bit of long division. So we can just do a bit of long division, I reckon, to simplify it a little bit. So 512, 16384, right? So we talked about how this part 512 wouldn't go into that. If it went into that, we would be timesing it by 3. So if we times it by 3, once again we would have gotten 6315, right? So we can say, all right, so that's 2, 0, 1, not 4, right? Okay, so 2014 is that just times 2, so 32. You can see that's that times 2, right? All right, so therefore we know that's going to be 32. So 32 would equal to R to the power of 5. R to the power of 5, so if we fifth root 32, 32 was just 2 to the power of 5, so R would just equal to 2. Okay, so then we can sub it back in to one of these to actually find what A is. So now that we know that's 2 to the power of 9, so that's going to be 512 equals to A, 2 to the power of 9, and 2 to the power of 9 is actually 519. So A will just equal to 1. And we can check that one more time. So I know that 2 to the power of 10 is equivalent to 1024. So therefore, if we times that by 2 again, we'll get 2048. And then 2 again, we'll get 4. So that's 11, that's 12. So that will be 4, that's 11, 12, so 4, 0, 9, 6, and then 13 would be 8, so that's 12, 1, 9, and then we can see that one would double into that, so we're happy with that. Okay, cool. So then what we're going to have is, so we now know that our equation Tn is equivalent to 1 r, let me just rub that out. So it's equivalent to a r n minus 1, and a is 1 and r is 2. So we can just put that in, so it's just 2 to the power of n minus 1. So 2 to the power of 51 is just going to equal to 2 to the power of 50. I'm not going to work out what that is because I think it's going to be a waste of both of our times, right? So just know that it's 2 to the power of 50, you can probably plug that into your calculator. Alright, so that's kind of the sequences itself, but let's talk about the sums of the sequences. So what I want you to remember is just have these formulas in your notes somewhere. So the sum of a sequence for the arithmetic sequence is kind of derived from the position that it's the first term plus, you can also write it as like the n over 2, a1 plus l, where l is the last term that you're working with. So as in a to the power of n. It can also be written like that. The geometric sequences, this is the general for this first term, for the nth term, sorry. But if you want the infinite sequence, a really important condition is that r has to basically be a fraction, and r evidently can't be 0 because otherwise it's not really going to be a ratio, but r has to be a fraction because then it kind of dwindles into nothingness at the end, and then you kind of get the equation that it's a over 1 minus r. Okay, cool. So let's kind of work through these a little bit together. So if we consider this sequence, a1 plus a squared plus a cubed, and tn plus 2 equals to tn. So we can kind of do that a little bit. So tn plus 2, right, is going to be, so if we just kind of pick a point, and that's t1, that's t2, that's t3, right, tn plus 1, we can kind of pick a point, so therefore tn would equal to let's say t3 would equal to t1 plus t2, right? That works, so therefore we can plug the points in. So a squared would be equivalent to a plus 1, right? So a squared minus a minus 1 equals to 0, so therefore you'll get that a will equal to 1 plus or minus root 1 squared minus 4, 1 negative 1 over 2. So a will equal to 1 plus or minus root 5 over 2, which is the golden ratio. Just for your information. Cool, awesome. Alright, so now they want us to do all the arithmetic sequences and find the sum. So the equation for the sum of n was equivalent to n over 2 2a plus n minus 1 times d. So therefore we would have n over 2 2a, so that's 2 times 2, plus n minus 1d. So d, we can see 3, 3, 3, 3. So that's times by 3. So we'll have n over 2, 4 plus 3n minus 3. So we'll have n over 2, 3n plus 1. Alright, so then we can sub in S15. So S15 equals to 15 over 2, 3 times 15 plus 1. So that's going to be 15 over 2, 46. And that's going to be 15 times 23. So 15 times 20 would be 300. 15 times 3 is 45. So we have 345 as our answer. Cool. Alright, so next is geometric sequence. So we want to find S10 and then S infinity. So Sn for this one, remember it's equivalent to a 1 minus Rn over 1 minus R, right? So we can say that a is going to be 1 here, 1 minus Rn, so 1 minus, we can see common difference is a half across, so it's going to be a half to the power of n. That's all going to be 1 minus 1 half, right? So we can see that's going to just be 1 minus 1 half n over 1 half, so it's going to just be 2, equivalent to 2 times 2 to the power of 1 half to the power of n. So then if we want to find S10, we're going to have, this is going to be equivalent to 2 minus 2 to the power of a half times 10. Once again, we know that 2 to the power of 10 was 1024, so we'll get that this is going to be 2 times 2, over 1024. So that's going to be 2 minus 1 over 512. So that's going to be 511 over 5. So it's going to be 1024 minus 1 over 512. So it's going to be 1023 over 512. Cool. Okay, and then S infinity is just equivalent to a over 1 minus r, and we can see that because this is a half, it's between the points of -1 to 1, so it's a fraction. So therefore we'll have here that this is going to be a, so 1 over 1 minus r, 1 minus a half. So our ultimate goal is to get to 2 essentially, which you can see this is already pretty close, but it'll get closer and closer and it'll probably never reach it. Okay. Alright, and that is the end. So we have a couple questions that you can kind of stick around for. There's a bit of advice, I guess, as well, but just this is the stuff we covered today: so simultaneous equations, discriminants, partial fractions, complex numbers, and sequences. So thanks so much for listening, and do make sure to ask any questions that you have. Thanks so much.